Well, while we're just making sure there are no late stragglers, we'll start off with this. So this is an animation. I just simply typed in to Google, I think climate change simulation, animation, I think I typed. Climate simulation animation. And this is from one particular climate model that contributed to the last IPCC process. This is actually quite a high resolution model, which I'll explain in a moment. This projector is terrible because you really can't see very well. I'm going to turn these lights off for a second. No, other way. Maybe that helps. Sorry, you won't see on the film, but you can see then the animation much more clearly. So what are we looking at here? What do you think the white colouring is? Clouds, exactly. And I think they're actually, I need to read the details, but I think the dark reds are illustrating where there's heavy precipitation. In other words, rainfall reaching the surface. This looks very much like what you would expect if you look at a satellite animation, okay? Because we have very smooth fields. So you'll understand what I mean by that in a moment. When these videos are made, the fields are kind of artificially almost tightened and smoothed. And you'll understand during today's lecture what I mean by that, because underlying this wonderfully continuous picture of clouds which are moving and advected by the flow, there's actually a discrete gridded resolution of blocks, of discrete blocks where we have a certain resolution below which we can't resolve details. So an analogy is when we watch the television, you know, when we look at the television, it looks like a perfectly smooth picture, okay? But if you actually go very close to the television screen is not made up of it's not a continuous line. It's actually made up of pixels, you know? You have pixels which can be set to a certain color, red or green or blue. So if you get very, very close to a TV screen, you can see it's actually made up, the picture, of small blocks like this, you know? It's just that because those blocks are very tiny, we don't really notice them from a distance. If you grew up when I did, the early computers had a very low resolution of what they could show on the screen. In the early 80s, a lot of the program, like the ZX81, I think just had a few hundred by a few hundred pixels. Then you could really see the blocks that made up what you were typing and what you were seeing on the screen. It was very... and nowadays, of course, the latest generation of televisions have gone to HD, high definition. So then even if you get very close, you can't really see the pixels because it's like a couple of thousand by a couple of thousand. Well, it's the same thing here, except that even if you get very close, the people that have made this video are very clever at making these pixels, smooth them out to an artificial high resolution that the climate model doesn't have. So today what I'm going to do is I'm going to explain this concept of the resolution and why it makes difficult life for people like me that want to treat the processes that occur in clouds, in climate and weather models. Yes?
First, is this to scale the time that is running up there?
Yeah. When you say it's to scale, you mean is it real time?
Is it real?
Well, it's the simulation time. Maybe try the question in a different way.
The time at which it is running.
Yes.
It becomes impossible to use, because normally when they are giving predictions, like what I've been seeing, say on CNN, BBC, they show those currents.
Yeah, this is speeded up, of course. So, I mean, each second is 1 day, because this is a climate model simulation, so they want to show many, many years, so it's clicking over very quickly. So you can see, oh, we've reached the end. you can see that the systems are moving extremely quickly, of course, as they come into Europe. I mean, if this were running real time, then these systems would be moving slowly across towards us. So the whole thing's just speeded up. It's like watching an animation of a car that's moving really quickly. I don't know if any of you saw the video on Tuesday evening about the history of Australia. Some of you maybe have seen that downstairs, and they show. So this is simulation time here. It's just running faster. I have another animation before I start the lecture, and the reason why I'm showing this is here this is much more low tech. Okay. So this is showing precipitation from another climate model, and now you can really start to see the blockiness, yeah? So this hasn't been artificially smoothed. So what I want to try and achieve today in today's lecture, we don't have that much time. I want to try and explain what's going on a little bit behind the scenes. So when you see people talking about climate models, you start to have an idea of what's under the bonnet, like in a car, what's really inside the motor. Obviously, I can't go down to every tiny little spark plug and every tiny wire. I can only go over in very broad concepts. But at least to have a rough idea of how these things are actually constructed. Okay? So, first of all, before we start, okay, it's driving me crazy. And now it's going to not do the presentation anymore, so I have to open it up again. I think it's when the mouse rolls off the top of the screen. So I'm going to very quickly remind you of the equation set, and you won't understand all of these equations because we haven't gone through the thermodynamics part, but just to give you the basics. So the thing I want to emphasize is that underlying fundamental equations that are solved are exact. They're derived from first principles. That's the thing you need to appreciate. When people say that models are uncertain, the basic, for example, equations of motions, these are the 5 equations. We have equations that describe, for example, how pressure gradients will accelerate masses of air. Okay? And these are just basic physical fundamental equations. Like if we know a car has a certain mass, we apply a certain force, we know what the acceleration is, and we know exactly how fast that car will be going after 5 seconds. It's the same for the atmosphere. We have the 5 equations are the equation of motion, the equation of state, the thermodynamic equation, the mass balance equation, and the water balance. Okay. Now, as I said, they're derived from first principles and they're certain. I've included them here, but I'm not going to spend much time on them. Okay. So, for example, the equation of motion, you might have seen this already with Fred, yes, for the large-scale dynamics, Fred Kucharski. So, for example, the rate of change of the velocity vector is impacted by if you have a pressure gradient. Okay, we have a change due to the rotation of the Earth, the Coriolis force. Okay, we have a gravity. Okay, so gravity, of course, affects the motions of the air, and F is a frictional term, so drag. Okay, and this is an exact equation. There's no controversy at all. Oops. And the other equations, I'm not going to dwell on them, but if you do the course with me next year on the Earth System Physics, the first term we have a course on thermodynamics, and I will introduce the equation of state that relates pressure to temperature. Most of you will already be familiar if you have a physics degree background, of course. The thermodynamic equation that describes how, if you have a change of heat, how we have it, that's divided between a change in temperature and work done, so a change in pressure. This is the form that's used in meteorology, so this will probably be less familiar to you in a physics background. We actually derive this from the physics form. We can't create or destroy mass, so we just have a simple conservation of mass. And this last one is for because we have a moist atmosphere, it simply says that the mass of water or cloud, liquid water or ice is conserved. So we'll have a number of sources and sinks. So we talked yesterday, for example, about how when cloud droplets bump and stick together, they make raindrops, okay? If you had one equation, this is called a prognostic equation because it basically says, it tells you how the quantity R, I, the mixing ratio, of liquid water changes in time. So we have a memory from one time to the next. And it says how, for example, the liquid water in small droplets change to rain droplets. And so you would have an equation that describes the rate of change from one category to another. Okay. And if all of those sources and sinks are 0, then the mass of liquid water droplets is conserved forward in time. Okay. So we have this simple, basic, fundamental set of equations, and they're derived and they are exact. Okay. So why is there controversy about, for example, climate models? And why do we have errors in, for example, weather forecasts, apart from chaos, of course? Well, let's go back to fundamentals. What are these things, these forecast models? Well, what we are trying to do is we have to basically solve this set of equations, these 5 equations, okay? But the first thing is, and I already introduced this concept yesterday a little bit, is we can't solve these equations like right down to the molecular level, okay? Because it's just simply not possible. So what we do is we introduce a concept that's known as the kind of continuum concept. So what we do is we take a gas, or if we were modeling a river flow, a liquid, and we introduce the concept of dividing it up into material volumes. I'm drawing it as a cube, just as an example, but we can have any material volume. So we have a surface that encloses a volume of the liquid or the gas. Okay. And we assume that this volume of the liquid or gas has uniform homogeneous properties, okay, of such quantities such as density, temperature, velocity, and so on. And so these quantities describe the state of this material volume, okay, the temperature. And within that material volume, we neglect all variability of those quantities, okay. And these state variables, such as temperature, will be a function of space and time. So we have a volume in a certain location, and it will evolve in time as well, and it can be moved around. Okay. Now, the other thing is that that equation set is not solvable analytically. Okay, so it's not like a simple equation where we can just write an exact solution. So we have to introduce a numerical method to actually solve this equation. So if we imagine this is time, okay? Let's imagine a simple system where we have like a car with a constant acceleration, okay? Or even, let's say, a constant velocity. If we have a constant velocity, and this is time, okay, and this is a space vector x, okay, we can solve Newton's equations, and we know that at a constant velocity, x will change constant in time, okay? So we can solve those equations, and we can say, given x0 at time t0, we know analytically exactly what x will be at any point in time, because we have the solution to this equation analytically. Okay. We could also solve those equations, should we say, numerically. And what that means is, given a rate of change of x, we solve it numerically by saying, okay, we know what dx by dt is, okay? And we just solve it by stepping the equation forward in time, okay, by a set time step. And we then estimate what that value is then, okay? So we can solve this analytically by just doing the integration. Or we can actually solve it numerically. So we can then discretize this. So this is at t plus delta t, okay, minus x at time t, which is time 0, okay, divided by delta t equals k, for example. So all I've done is I've discretized this equation, and then I can rearrange this to give me x at t plus delta t equals k times delta t plus x of t. So for a given change in time, delta t, I step forward and work out the new value. Okay, and this is called the time step. Okay. Now those of you staying on to do the full diploma will see that this is actually a very bad way to solve this equation. Okay, because once things get complicated, this discretization I've done is actually unstable in most kinds of equations, okay? But that's detail. Don't worry about that for the moment. I just want to illustrate this concept of discretizing an equation, okay? And so with a atmospheric model, that equation set cannot be solved analytically. We can only do it in this way, by taking these differentials in the equations and splitting them up into discrete time steps and using numerical methods to step forward in time. So we say, this is the state now, okay, at 11:15. And then we take a step forward and say, what is the new state in half an hour's time at 11:45? And we're assuming that during that half an hour, everything remains constant, the evolution, okay, to a first approximation, just to keep things simple. You can use advanced numerical methods that also assume that things change during the time step in a way that you can describe. But just for the moment, just imagine this constant step forward. So you say now, in 1 hour's time, in the next hour's time. So you're doing discrete steps forward in time. Okay. So again, this is just like the equation on the board. This is just a very simple equation for a Newtonian relaxation. So we have like temperature T, okay, is relaxing back at a rate that's actually related to temperature itself. So we have dt by dt equals minus t over k, and k is just a constant. Okay. And I've just split this up, and as I say here, this is not a good method in general. Right? This is just a very simple method to illustrate this, and it works for this very simple equation. So just in the same way, I've used a slightly different notation. N is at a certain time level, n, and n plus 1 means at the next time step forward in time, okay? Oh. Which one is it? This one? Okay. Still there. Good. Okay. So all I've done is discretize this equation. I've written it in discrete steps. The time at the future level minus the present time divided by a discrete time step is proportional to t over k, and I'm taking t at the present time. Okay?
Question. Going back to when, if really, or like as you mentioned, that there are other fair methods we can use and we step forward, then it should be equally. We can also step backwards.
In this case, you could actually write the inverse of the equation and step backwards. You can write in what's called an adjoint model. But in general, adjoint models, you can only write for linear systems. This wasn't a linear equation that I've just written. So then you can write an inverse. For nonlinear equation sets, it's generally very difficult to write the adjoint, the inverse of the model. So you can write, if you have like dt by dt equals, well, let's have a look, t squared, okay? Then you can take a linear approximation to that. So the linear approximation to that is basically you just differentiate it and you get 2t. And then the inverse of that is just t over 2. So you can actually write adjoint models. But you can only do that for linear systems. Okay, that's an advanced question though. We use that in data assimilation, by the way. When you actually want to, data assimilation is when you take all of the observations and try and work out the state of the atmosphere.
But are there some parameters in data which are changing? Because Fred was saying that most of the time,
I'm not sure I'm understanding the question then. I mean, basically, if you have a linear system of equations, you can step them forwards or backwards in time. Okay, that's an example where I'm going forwards in time. But if you can write the inverse system, you can also go backwards in time. So from this state, you can integrate the equations backwards. But that equation set for the atmosphere, you can't write the inverse model of that because it's a nonlinear system. Okay, you'd have to linearize those equations first. So if you have a nonlinear equation, you take a tangent linear, and then you can write the inverse of that tangent linear, and you can go backwards. So we do that in data assimilation. But anyway, let's just keep things simple and then go forwards in time for the moment, okay? Before we get too complicated. So this is a discretization of that simple equation, okay? And now we have a choice. And the reason why I'm going through all this, you're thinking, why are we talking about this? Well, the point is, we have a choice of this time step. We could take a very small time step and just go a little way into the future, or we could take a big time step and go a big way into the future. Okay. So why would we want to take a really big time step into the future? We want to solve this for the next, let's say we want to solve this equation to see how temperature will evolve over the next day. Now, we could solve it with a step of 1 hour, or 1 minute, or 10 seconds. Why would we prefer to solve it with a step of an hour instead of a step of a minute? Not necessarily data. Do you want you were?
I think within an hour, some changes will have taken place as compared to when just a minute.
But if you do 60 steps of a minute, you probably expect, if the equation is the same, hopefully if it's accurate, you would have the same solution after an hour for 60 steps of a minute compared to just 1 step of an hour. So what do you think then? You had your hand up next. Exactly. So if we manage, each time we take a minus or a division, it's one calculation in the computer. And just like more things that we do, it takes more time. Same for the computer. So if we go forward 1 hour, okay, fantastic. We've only done one set of calculations. And that means that it's more efficient than taking lots of little steps. Okay. But is it as accurate? Well, let's have a look. Okay. Well, I've normalized this. Rather than being in minutes, this is just a fractional time step, okay? Because this is I've just done it in a normalized coordinates. I won't explain what that means, but let's just say we take a normalized time step of 0.05. And so each of these red circles is a step forward of the solution. The black line is the analytical solution. So remember, for the climate model, when we're modeling the atmosphere, we don't have the luxury of knowing what the exact solution is because we can't solve those equations analytically. But this is a simple illustration, so I can solve the equation, and I just have this exponential decay. Okay? And then what I've done now is I've integrated that discrete numerical equation forward in time. Okay? And this is my red solution, is my numerical solution. Okay, it looks quite good, yes? I mean, there's not a big difference. And after 5 normalized units of time, I'm arriving at the same point. Okay, and this is with very small time steps. So the solution is stable, and I would say it's quite accurate. Okay. Now I've made the time step 10 times longer. Okay, and this is my solution I get. So it's still tending towards the same final values. But you can see that compared to the last solution, it's less accurate, yeah? The difference between the analytical solution and my numerical solution is quite large. Okay. So I would say the solution now is still stable, but it's perhaps inaccurate. I mean, this solution here, this is quite a big percentage error. Okay. Now, this was at 0.5. Let's make the time step, again, 3 times longer. I think the next one, 3 times longer. Now what's happening? Not only is it extremely inaccurate, it's even unstable. Okay. And in fact, you even have situations sometimes where this is oscillating. but at least the oscillations are getting smaller. You can have situations where the oscillations just get bigger and bigger, and the whole thing just blows up, okay, because you get infinite solutions. So we had three choices. Very small, it was very accurate and stable. Then I made it longer by 10 times, and it becomes inaccurate, but it's still stable. And then here, we have an unstable solution. So which time step would you use? 0.5, 1.5, or 0.05? Do you all use this one? Okay. Well, the answer is not so clear. And we'll see why in a moment. Because sometimes, if you can have 10 times as much computer power to spend in other issues, and I'm going to talk about one of them next, sometimes maybe you can live with a little bit of inaccuracy, okay, if that gives you a lot of extra computer. And don't forget, this solution here is 10 times more expensive, okay. So the answer is not so clear. So we're going to see why as we go through today's lesson. But this, even though this is an extremely simple example, these are the questions that we have to address all the time. Now, and again, I should emphasize that this particular numerical method is not very good. I could have, for example, if I'd taken t here, instead at level time n, if I'd taken it at n plus 1, the solution would have still been stable even at the time step of 1.5. But it would be very inaccurate, okay, but stable. So when you're constructing these climate models, there's always a choice, and people are always trying to improve the numerical methods to solve the equations in such a way that they improve the accuracy, but they also improve the stability to have longer and longer time steps, you see, in order to be able to save the computer time to spend in other ways.
According for all the three steps that we have seen, it shows that after some times, normally, both results come closer as time goes on.
Yes.
Yes, how do you explain that?
Well, it's because it's an exponential decay. Now, as you look at this solution, okay, it looks like they both converge because by construction it's converging to 0, okay, and we have a stable solution. However, the relative error, and I haven't checked this actually, but I suspect that the relative error is not decreasing. So from I, this looks, for example, like the error is getting smaller. But if you look this, in relative terms, here we only have half of the correct solution, okay? So probably if you look here, the actual percentage error is even larger here than it is here, even though in absolute terms it's smaller. And that's just because this simple equation is constrained to just exponentially decay. But if you looked at the relative error in percentage terms, it's probably increasing as time goes on, okay? Yes. Hmm.
But the data also is not actually in use from results. How do you compare the accuracy?
And that's a very good question, and there's not an obvious clear answer, okay? But what you can do is, for example, if you're concentrating on a certain component, you can try and isolate that component in an idealized test where even if you don't have an analytical solution, or maybe for that idealized test you even can produce an analytical solution. It's a little bit like when we talked about generalizing the slab model. When you get your final equation, you should always think of a special case that goes back to a solution that you already know. So one example could be, if you imagine the planet, and we have maybe the momentum advection equations. You want to change the way the advection equation is just the movement by the flow of a certain substance. So say you have a moisture anomaly, okay. You could try and turn off all of the other physics, like all the clouds and convection and so on, and you just want to concentrate on one aspect. And so you have a moisture anomaly. You can start it at the equator, and you can fix the model to have, for example, a constant velocity u. Okay. So what happens to this moisture anomaly? You expect it to move at a constant velocity and arrive here. And so that's a simple idealized test where you've kind of reduced the system to a kind of linear system where you just have a linear constant velocity that moves this feature from here to here, a little bit like the simple case. And then you can test your different numerical solutions. And if one gives you a very noisy edge or a very diffuse, and another one gives you a very similar pattern to the one you expect, you know that this one is a better numerical solution. Okay. Now, you can only test it, you're testing it in an idealized case with a constant velocity. And then, of course, when you allow the velocities to change non-linearly, you have accelerations and so on, then you don't know exactly what you expect to have anymore. So what you're trying to do is you're trying to set up idealized situations that you can test. And if you improve those situations, you hope that in the full non-linear system, you're also doing a better job. Okay. And of course, you try and compare the model to data and so on. But it's always best to start off with a simple situation like this. And not everybody always does that. Often you find people change things in climate models and they don't go back to first principles for the testing. Okay, so, and I'm a strong believer of this. So there's not a right way of doing this. And I always believe that with any complex system, when you change things, you should always try and go back to the fundamental nuts and bolts and try and set up simple tests to make sure you understand what you've changed and how it's working. Okay. Now, how else could we spend the computer time? Well, it comes down to this mesh of these grids. So this discretization, that example I had, was not an equation that was solved spatially. We just had simple one value of temperature, and we wanted to see how it changed in time. But of course, what we're concerned with the climate models is solving this equation set for the whole 3D atmosphere. Okay. So we might have some area of the atmosphere. And so what we do is, we talked about this concept of the material volume, is we divide this area, which might be the whole globe of the atmosphere. It might just be the atmosphere over Friuli, Venezia Giulia, or over Italy. And we divide it into sub-cubes, like an array of meshes. And each one of these is like a material volume. So all we know is for each of these sub-cubes, we have one value for temperature, one value for humidity, one value for the velocity vector, one value for the density. Okay. And there's no variability on the sub-cube level, the sub-volume level. So the only way that temperature changes is the way that the temperature changes is between the different boxes. Okay. So, for example, a simple discretization of the globe could look like this, where we divide the globe's atmosphere into an array of latitude and longitude lines. And it's a 3D decomposition, so we also have cubes in the height, so in each direction. Okay. Now, of course, this is just one example. As well as the time step for the equations, okay, the more computing time we have, the smaller we can afford to make those boxes. So if you imagine, let's go back to this example. Here we have a box that's like 3 by 6. So in the horizontal we have 18 boxes. Now, we can only resolve the variability, so by that represent the variability on scales of the size of this box. So we only have 6 points. So if you have a continuous function that looks like this, you're going to represent it just by 6 points. So you might have a value here, a value here, a value here, a value here, so on. Okay. So what does our representation of this continuous function look like? It looks like this. You see? So all of the fluctuations on smaller scales are ignored. Now, if we had more computer time, we could afford to maybe have smaller boxes, and we might be able to start resolving some of this variability and presenting smaller scale fluctuations. Okay. So So this is just one example of a very simple simulation of a flow, just a rotating vortex. And I'm not going to dwell on it very long, but it's just one example to show you how these small-scale eddies and vortices are represented with a 62-meter resolution, and they're completely absent here. But of course, this will be much, much, much more expensive to run than this one here, okay? Because you have more than 10 times as many points in each direction. And I'm not going to go into detail, but the smaller the boxes are, for most numerical methods of solving, the smaller that stability limit becomes for the time step. So for small boxes, you need a small time step. For large boxes, you can have a larger time step. So if you half the resolution, okay, it's normally a factor of 2 cubed for the expense, because if you half the size of the boxes, you double the cost, because you've got twice as many calculations. Double the cost, twice as many calculations. Plus, the time step needs to be half the size, so you need twice as many steps. So you double the number of calculations again. 2 times 2 times 2. 8 times more expensive just to go from a box of 200 meters to 100 meters, okay, in the horizontal. So this is the point I'm saying here. How fine of a mesh can we use? Well, it depends on the computer resources that we have available to us and how we want to spend those. So at the moment, global climate models tend to use grid sizes of around 100 to 300 kilometers. For AR5, the next IPCC report, some global models, climate models, are starting to come below that 100-kilometer grid size. Okay. So think about that just for a moment, 100 kilometers. Okay. How far is it from here to Ordina? It's about 60 kilometers, yeah? So that means that the temperature in Ordina, in one of these climate boxes, will be the same as the temperature in Trieste. It's all within the same box. All of the subgrid variability is ignored, whether it's the point over the ocean, over the bay, or over the castle. And you just think, in winter here, I can drive. My car has a temperature gauge, and in winter, when you have stable conditions, I can drive from here to Opicina, and the temperature can drop by 5 degrees. Okay, in 4 kilometers, just going up the hill to Opicina. That's all within the same box. So all of that small-scale variability will be ignored. Global weather forecast models tend to use boxes that run from 25 to 50 kilometers. The centre I used to work at, ECMWF in Reading, actually is down at 15 kilometers now. That's they have the kind of biggest computer available for meteorology applications. And the reason why they can have those smaller boxes is they're running the computer model simulation for forecasts of just days, instead of a climate model that needs to have many steps going out for tens, if not hundreds of years into the future. Okay. So the number of calculations is fewer. Okay. So this, for example, for those of you interested in the climate aspect, is showing the different representative resolutions that were used in the IPCC climate model simulations. So FAR stands for the first assessment report. So this is the, if I remember rightly, this is the simulations were carried out in the early 1990s. So they're roughly 20 years old. And we had resolutions at that time on the order of 500 kilometers. Okay. Now, if I asked you, without looking at the other should we say, the other pictures, just this top left picture, if I asked you where on the planet this was, it would be pretty difficult to say, no? The location. Okay. Now, I was actually born right in the middle of the sea here, according to this map, okay? Because Great Britain is not even on the map, you see, it's not even resolved. We're just not there, okay? So I'm sure there's lots of political jokes you can make about that, but as we're being filmed, I should refrain from it. But we can see now we're going from the first to the second report, okay? Now the English are happy because there's England on the map, but no Scotland. And if you want to go and buy some cheap wine in France, you can just happily walk down, like there's no problem at all. because of course the English Channel is not resolved. Okay, but at least the Mediterranean is starting to look, you know, approximately like it is now. Again, where's Italy on this map? Okay, so not only are we not resolving the Apennine or the Alps, we don't even see Italy properly, no? By the third assessment report, we start to see the Alps. Italy becomes visible. Britain is starting to look roughly like it is. Look how the topography is much more clearly resolved, for example, over Greenland. The fourth assessment report, we're under 100 kilometers. Okay, and this is the situation for the resolution. So you can imagine that resolving these mountains is quite important to resolve the way that the flow is interacting with the topography, whether the airflow is lifted over the mountains or goes around, the triggering of convecting storms. This is an example over Europe, but of course it's valid wherever you look on the globe. Ethiopia, at this resolution here, you wouldn't resolve the highlands, you can't resolve the complexities of the Rift Valley. Okay. So this is an example, for example, of how increasing the resolution from 300 kilometers down to 25 kilometers slowly improves the precipitation climatology, the rainfall climatology over Britain compared to observations, you see. At 300 kilometers, the whole topographical forcing of the precipitation is just completely absent. Whereas at the 25 kilometers, we can see the rainfall generation very clearly. Okay. And again, this is just another example. I don't want to dwell on it, but this is 200 kilometers, and this is a small regional scale simulation at 10 kilometers off the west coast of the United States. Okay. And this is the reanalysis, and you can see that this rotary vortex flow, due to this topographical shape of the coastline, is simulated well at 10 kilometer box sizes, but you just don't see it at all at 200, of course. Okay, and this is a satellite picture that actually shows the low-level cloud wrapping up inside this vortex flow in the satellite, just to show that the reanalysis, the models. When we say reanalysis or analysis, this is talking about data assimilation, where it's using the model to try and assimilate all of the different observational sources, like ground measurements, measurements under balloons, where we launch balloons every day and they have a temperature and humidity gauge underneath. For example, satellite information. And it tries to merge all of those together into a picture of what we think the atmosphere state is right now in each step. It's actually a very complicated engineering, should we say, task if you think about it, because all of these different platforms measure very different quantities with very different sampling rates. And so you have to try and merge them all in together into a stable, self-consistent, physically self-consistent picture of the atmosphere. So this is what this is here. So this comes back to this issue. We talked about the time step choice. Okay, so we have all sorts of ways in which we can choose to spend our computer power. We could have...
Sir, okay, when we make 12 log reads, okay, besides the problem in the time scale, there is an inherent precision problem in the numbers, right? When we have more reads, we'll do more calculations in each read, and then more operations, and then we'll have some precision problems in the numbers, right?
No, you would hope not. If you're resolving the should we say, the variability, the only case that occurs is for certain numerical solutions, for example, if you take sometimes shorter time steps. If you have a certain way of solving the equations, I don't want to go into details, but where you have a kind of constant error. So one example is semi-Lagrangian advection schemes. Then the more steps you do, the more accumulated error you actually have, okay, by having shorter steps. But that's a special case. In general, by resolving the variability, you make less truncation error, okay. So this is this thing here, you see? You're making more truncation error by having a lower resolution. So we have to make a decision, you know, would you spend the time on having shorter time steps, which in general gives you less error. There's just certain special cases for certain kinds of equation. But in general, if you have shorter time steps, you have a more accurate solution. Or you can spend it on having smaller boxes, you see. This is play out. However, there's also a third way you can spend the computer time. Okay. Oh, I forgot to mention this. Yeah, so a typical global model uses a time step between 10 minutes and an hour, whereas some of these smaller scale regional models will be using time steps of just minutes. Okay. So there's a third way, and this is what I want to talk about in the remainder of this lecture. Okay. So we've talked about these box sizes, but there's another problem now, because we talked about having a box size of 100 kilometers, which means we said that the temperature represented in ordinate is the same as the temperature here. But we also have another problem, which we've kind of mentioned already during the course. What else is the problem? This is the one I mentioned here, is that some processes are occurring on very small scales. Okay. So one example I mentioned before, the thunderstorms. So the kind of thunderstorms that we've been experiencing, okay, even their, well, you tell me, I mean, their dimension, if you have one of these deep thunderstorms, the dimension of the anvil cloud is maybe measured in terms of kilometers. Maybe you'll reach 10 kilometers. If you watch one of these storms coming, maybe you'll see the edges of the cloud will be over Trieste, the other side will be over the other side of the bay, over Monfalcone. And then the actual velocities and these sharp updrafts and downdrafts, I mean, this kind of updraft core where you have the intense rainfall is only on the order of a kilometer across. And in fact, these circulations are varying on much smaller scales. So all of the transport of the air going up very rapidly and then coming down very rapidly within these clouds is occurring on very small spatial scales, on the order of a kilometer. So it's very small compared to one of these box sizes. So you can't represent these motions in each of these boxes because you have these discrete sets of boxes that are 100 kilometers across. And the velocity is either upwards, downwards, or zero. So either all of the air is going up or all of the air is going down. Whereas in reality, we have these storms occurring where the air in a small proportion is going up and going down, plus you have some slow compensating substance around the cloud. Okay. So what are the kind of processes? Well, we've talked about some of these already in the course. Okay. Not all of them, but turbulence we talked about, you know, when we have a heated surface, the bumpiness of the aircraft. This is transporting energy in water vapor. Okay. But it's small-scale eddies and overturning circulations. Deep convective clouds. So we talked about the way that the droplets form rain droplets and fall out. But this is all happening on small spatial scales. So the cloud processes themselves. And then the radiation interaction with these. So all of these processes are occurring on small spatial scales. Okay. And so we need to represent these in the model. Why do we need to represent them? Well, as I said, what's the purpose? Why are these storms occurring? We talked about that. If we didn't have any motions, essentially what happens is the atmosphere is cooling by infrared radiation. The surface is warming because it's heated by the sun. So we have a hot surface, a cool atmosphere, and essentially that situation becomes unstable. Hot air, cold above. The hot air is lighter, it rises. The cooler air sinks. As it rises, it cools, expands, it cools. So we reach saturation, and we have these cloud processes occurring. Okay. If we didn't represent those in the model, what happens? The model on 100 kilometers gets cooler by radiation. The surface is warmed until all of a sudden, bang, we have one gigantic storm where all of the air over 100 kilometers is going up at 10 meters per second. You know, the most enormous storm that you would ever experience ever. Can you imagine a whole 100 kilometers going up at 10 meters per second? Okay. What happens? The model just blows up. It can't handle that. It's just crazy. We get a ridiculous solution. It'd be like all of the storms wrapped up into one big storm locally of 100 kilometers in scale. So we need to prevent those instabilities. We need to represent these processes. Okay. So what we need to do is within our global model, inside each of these boxes, we need to represent these processes by like a mini model, like a small model that's inserted to represent those processes. And that mini model is called a parameterization. So most of my research career I've actually spent working on this problem of how you represent processes such as clouds inside the global models, in these little mini models called parameterizations. Okay. Now, in order to explain that, I'm now going to go through, in the next 40 minutes, okay, an example, and a simple example, but mathematically derive it. Okay. And I think this is quite important to realize that there is a mathematical basis to this model, these models, but there are also decisions that you have to make that are kind of ad hoc because you have parameters that you need to set that you can't easily measure outside. And so you have to perhaps try and tune those parameters, choose a value that best improves the simulation of the global model. And that's one of the big causes of the question mark, the uncertainty of these models. Okay. So that's what I want to try and put across. And so I need to do that deriving these mathematically. Okay. And I'm going to choose the equation set with those 5 equations is complicated. So I'm going to choose a very simple equation to explain this, which is the vorticity equation. Okay. And this is relevant. The very first, back in the 1950s, the very first weather forecast model was based on this equation. I think it was 1950 it was made. And so this is a very simplified version of those sets of equations that describe the atmosphere. It's dry. We don't have any equation for humidity. Okay. All we have is one equation that describes the rotation in the atmosphere, the vorticity. Okay. And it has just 3 components. We have the rate of change of vorticity, how it changes with time. And okay, it's going to be resolved in these boxes, so it'll also be a function of space. Okay. And the rate of change essentially has just 2 components. We have the motion at vecting vorticity, so moving the vorticity along. So if you're rotating, if you imagine a low pressure system, we can move it by the mean wind, for example. And this is the Coriolis effect that just tells you how the rotation changes if you move towards the pole or away from the pole due to the rotation of the Earth. Okay. So we just have the rotation impact and the advection. Okay. Even if you don't fully understand this, it doesn't matter. The concept will be clear nevertheless, even if you don't understand the exact origin of this equation. I'm just using it for an example. Okay. Now, so v is the velocity vector. I should have written it here actually with an underbar because that's the notation I use. I've used bold font then. Sorry, I have to change that. I didn't notice that before. So this is the velocity vector, and this is the quantity that I'm vecting, vorticity, just the rotation. In fact, you could also, if this were temperature or humidity, it doesn't really matter. Okay, it's just a velocity vector and a quantity that we're interested in. Okay. So this, as I've written it, is an exact equation, just like those first 5 equations. It's an exact equation that is describing the atmosphere in a continuous sense. I haven't discretized the equation into boxes or anything. Forget about the boxes. Forget about the time steps. This is just a simple vorticity equation that tells me how vorticity is changing in time. Okay. So now I'm going to solve it on my boxes. Okay? And so what I'm going to do is this continuous equation. So you imagine I can have vorticity, it could be temperature or humidity or whatever. is changing in space continuously. Let's imagine it's temperature, for example. If vorticity is confusing for you, just imagine temperature. Temperature is changing continuously in space, yeah? So if I move from here, as I move towards the sea, if I carry a thermometer, that thermometer will slowly change as I move in space, because probably the temperature is closer, is different in Miramar Castle than it is here. The differences will be very small, but as I move with my thermometer, the temperature is changing continuously in space, yes? Okay. Now what I'm going to do is I want to discretize this quantity, vorticity or temperature, into these boxes, okay? So what I'm going to do is I'm going to split my continuous function up into two components. The mean over the box, and then the local perturbation. So this is why I've tried to draw this cartoon here to illustrate this. This is my continuous function, okay? And what I've done is this is my box, okay, which I've chosen of a certain size, and this is another box. So imagine this is just one dimension in my climate model or my forecast model. And so what I can say is that every point, I can say that the continuous function value of temperature is the grid box mean plus a local perturbation. Okay, so we have the grid box mean plus a local perturbation. So this is my continuous function, like this. Sorry, I forgot to use the mouse. And we have the grid box mean and a local perturbation. So for example, vorticity, I write vorticity equals the grid box mean plus the perturbation. Yes? Okay. What's over a grid box? What will be the sum of the perturbations over the grid box? 0. By definition, it's 0, because this is my grid box mean, yeah? So over, if I walk from here to here and I add up all of these perturbations, by definition, they add up to 0 by construction, okay? And as I said, I can do this for every variable. So if I'm worried about temperature, I have a temperature equation. I can do the same thing. Velocity, every parameter I'm interested in, I can divide it up into a grid box mean and a local perturbation. Okay, and this is useful because now I'm going to carry out a process called Reynolds averaging. Have any of you come across this before in any of the other course components or your previous physics degree? Okay, so this looks pretty complicated, yeah? So where's this come from? What I've done is I've taken this, the mouse is going to drop off the top and then everything goes terribly wrong. So what I've done is I've just simply taken my equation and I've rewritten it using this discretization. Oops, what have I done here? My psi is terrible, sorry. So d psi by dt, for example, I can just write it this way, no? I can say it's basically plus the perturbation. So these are partial derivatives. So then I can just write it as the two components, yeah? Okay, it's the same with temperature. So all I've done is the same for all of these, okay? I've got 3 terms here, but I don't get 6 terms in the final equation because here I have a product. So I've got V bar plus V perturbation multiplied by this. So this gives me 4 terms, of course, because I've got bar bar, perturbation bar, bar perturbation plus perturbation perturbation. Yes? Okay. So this equation, all I've done here, it looks horrible, especially because I've changed my notation here. I apologize for that. But this is just the first term. Then I've got 4 terms because of this product. Okay? And then my correlasis is very simple. I've just got beta, which is a constant, times the grid mean value plus beta times the perturbation value. Okay. Why has this helped? And the next thing I want to do is I want to take an average over the grid box and over a time step. Okay. And now we'll find that some of these terms will disappear. Okay. For example, if I have a perturbation, so like T perturbation, if I average it over the grid box, what happens? What do I get? 0 by definition. Okay. If I have a perturbation and I multiply it by a constant and I average over the grid box, what do I get? 0. Okay. So if I have a bar quantity multiplied by a perturbation, what do I get? 0. Okay. This is fun, no? What about if I get 2 perturbation quantities and I average them over a grid box? What do I get? Say again? We don't know. Okay. It could be 0. In which situation would it be 0? This is a tough question. I'm not. Can any of you kind of think of when would you get this to be 0?
The mean of the product is equal to the product of the individual mean.
Yes, which means? They're independent, exactly. They're uncorrelated. Exactly. Very good. So if they're uncorrelated, then this will also be 0. But if we have correlations, so say the v velocity is negative here and positive here, okay, and then the t has something like this. So here, okay, they're in the same direction, here in the opposite, and here in the opposite. But if we add up all of these, we find we have a net flux, yes? Same as if I draw it this way. So we have negative with negative, positive with positive. So positive velocity carrying positive perturbations upwards, negative velocity carrying negative perturbations downwards. We have a net transport, yes? Okay. So it's not 0. Very good. So everyone's following me. This is excellent. So what happens to those equations, if we go back to the previous page, we just average over all of these. This term here drops out, yeah? This term drops out. This is 0. Because we have a bar with a perturbation. 0, 0. What are we left with? An equation with 4 terms. Okay. Everyone's with me so far, why those perturbations drop out to 0. Now, if we look at this, this looks quite familiar, yes? In fact, if we compare it to the original continuous equation, we have exactly the same terms, this, this, and this, except that now, rather than a continuous variable, we just have the grid box mean. Yeah? This is the mean, the mean, the mean, and the mean. Okay, so the equation is exactly the same as the continuous equation, except that now it's written in terms of grid box mean values, averages over time steps. Okay, so it's a discretized. But there's one sticky, thorny problem. We've got one new extra term. Yes? This little character here, this third term. Okay. What does this represent? Well, this is all of that annoying small-scale stuff, yeah, that's occurring. This is saying if we've got perturbations in velocity that are happening on small scales and they're correlated with perturbations in the quantity that we're interested in, be it vorticity or temperature or whatever, then we have a net flux on the small scale, okay, that we need to consider. So this is all that small-scale stuff. So we've split the equation up into 3 terms that describe what's going on the grid mean, plus 1 term that conveniently partitions up everything that's happening on the small scales. Okay. So this represents, in this particular equation, the effect of all of those small-scale motions. Okay. You all with me so far? Okay. So now we need to take another step. Okay. What we need to do is, okay, we don't know what v dash is, because that's the small-scale velocities, yeah? And we don't know what, like, our temperature perturbations are, because we can't resolve with our boxes this function. So we don't know what those fluctuations are in each box at each time. Okay. So we're a little bit stuck. What can we do? So what we want to do is that we can say, okay, we don't know the nature of those fluctuations, okay, but is it possible to describe what we think the statistics of those fluctuations will be given the large-scale resolved situation? Okay. So what that means is, what we want to do is we want to say, can we sensibly think of a function h that allows us to describe the net average behavior of this term as a function of the variables that we do know on the resolved scale? In other words, can we describe the small scale behavior knowing what the large scale resolved equations are? Okay. Why do we want to do that? Because if we can do that, okay, this term here, we've got h of v dash psi dash, yeah? If I go back here, if I write that term in there, we know what that function h is. We've closed the problem. So when we say closure, of course, probably you've come across that expression before. At the moment, this is not closed because we have parameters that we don't know. If we know what that function h is, now the equation is written all in terms of grid average parameters. And we can then integrate that equation numerically forward and make our forecast. And the function h is describing the action of the small scale variability in terms of the grid scale variables. Okay. So I'm going to now, so this function h, okay, is our parameterization. So if you hear people talking about climate models or weather models, basically, and they talk about parameterizations, now you know what they are talking about. A parameterization is like a small model. You remember, just remember that slide. This is the really important one. It's a function h that just simply relates what's going on in the small scales to the grid scale variables. Okay, so it's describing the statistics of those small scale processes. And that's a parameterization. And they can be very simple or they can be very complicated. They can be quite physically derived or they can be quite ad hoc. Okay. So I'm going to give you now a simple example, okay, of a parameterization which is quite physically based. And then I'm going to give you an example of perhaps a slightly more ad hoc one, but nevertheless physically based, okay, to do with clouds. So we attempt to construct a series of physical models because we won't just have one model h, because we have lots of h functions for all of the different processes. Remember that schematic. We've got deep convection clouds, we've got these precipitation processes, we have radiation interaction with clouds. So these functions h can get quite complicated. Okay. And this is the parameterization task I've spent a lot of my research life involved with. Okay. And so what we're going to do now is we're going to discuss two examples, turbulence and clouds. So they're two fairly simple examples because we don't have that much time, but it's to show you the concept of the parameterization task. Okay. Parameterizations that represent deep convection, for example, can be very long. You can get parameterization functions h that can be easily 2,000 lines of Fortran code and sets of instructions, you know. So these examples I'm giving you are very simple functions, okay. And let's start off with turbulence, the bumpy landing of the aircraft, okay. So I'm going to give you a simple example of this, where I'm going to represent the transport of a quantity, such as temperature or vorticity, just by these small-scale turbulent motions. Okay. So when we have turbulent motions in the boundary layer, okay, we want to describe the statistics of what that turbulent motion is actually doing. Okay. So let's make, before we show the slide, let's just think about it for a moment. Remember I gave that kind of an analogy yesterday when I said about diffusion. Let's imagine I have a box here in the corner that has a blue gas, a colored gas. I slide open the door to release the gas, okay? And then I wait for maybe a day or two or a week. Would the blue gas remain in the corner of the room? What happens? Okay. It would mix throughout the room slowly, yeah, just by Brownian motion. If I came back after a week, I'd expect that the blue gas would be almost uniform within the room, okay, just by small-scale motions So we can imagine that turbulent small-scale motions, if we started off with a concentration as a function of x that looked like this, after a period of time we'd have a uniform distribution. So what have we done? We've actually, the turbulent motions are moving high concentrations here and they're moving some low concentrations here. So what are they doing? They're smoothing out this gradient. Okay. Now, it doesn't have to happen that way. You can imagine if you have high concentrations and low concentrations and you have a mixture, you can sometimes maybe have situations where gradients are sharpened, and that does happen. But in general, we can say that the statistics of turbulence, we can make an analogy, a hypothesis, that they will generally smooth out gradients. So we have a high concentration, a low concentration, and we mix up. You imagine like a pot, and we mix with a spoon. What happens is we mix everything up and smooth out the gradients, so we have a uniform distribution. Okay. So if we wait long enough, the effect of the subgrid scale variability will be eventually to give us a state where we have no gradient. So the rate of change as a function of space will be 0. Okay. So I'm going to make a hypothesis. I'm going to say, let me derive a parameterization that represents this. So I am going to take this term for the correlation, so this is the flux, and I'm going to assume that the flux, the transport flux on the small scales, is simply related to the gradient. Okay. So if I have a strong gradient on the resolved scale, let's imagine, so this is one box, and this is another box. The small scale turbulent motions are trying to, if you imagine this is part of, we have a continuous function, so we have a high concentration and a low concentration. What it's trying to do is smooth out this gradient, both on the small and the large scales. So if I have a strong gradient between these two boxes, so I have a high value here and a low value here, my assumption is also that we have a gradient on the small scales. I think someone's probably ordering a pizza. Pronto? Hi, I'm in the middle of a lesson. I don't know who you're trying to call. Hi. I think it's the wrong number, yes. Thanks a lot. Bye-bye. These videos are going to be just like, we can sell them on a comedy show. No, I think we have to edit this out as well. Anyway, it wasn't a pizza, by the way. Okay, let's try. Obviously the wrong number. Okay. Yeah, that's a good idea, actually. Okay. Where was I? Once I get on a roll, we see if I get distracted and I lose it altogether. So what I'm going to do is I'm going to assume that the flux is related to the gradient. So if we don't have any gradient on the large scale, I'm assuming I don't have any gradient on the small scales. Okay. And so if I have no gradient, it's already uniform. So let's imagine that this blue gas is already well mixed. I can take the biggest spoon I like, I can mix as much as I like, but no matter how much I mix, it's already uniform mixed, yeah? So all I'm doing is moving around material volumes with the same quantity of the blue gas. It's not going to change, okay? And so in that case, the flux, net flux, will be 0. If it's uniformly distributed, if I move some air there and some air there, it doesn't change anything. I'm moving some there, they cancel out. We have no net flux. Okay. And so I'm relating the flux to the gradient by a constant k. Okay. So it's a constant. So k, I'm going to call the diffusion coefficient, and it represents the strength of the eddies. So if I'm mixing this room with a giant spoon, it's basically k is the size of my spoon. It's saying how much I'm mixing, yeah? So if I have a small gradient but a very big spoon, I have a certain flux, or I might have a large gradient and a small spoon. The flux then is the same. Okay. So K describes how strong the eddies are. Okay. And I'm just going to fix it by constant. I'm going to say, I think my eddies, my motions, should we say, like this turbulence, has a certain strength, which I'm going to fix and define K to be a constant. And so then I'm describing the flux just in terms of the resolved gradient. Okay, is that clear? So I'm assuming with a constant K that my turbulent activity is always constant. So now if I take the gradient of that, because remember, if you go back to the equation, yeah, we have grad dot, yeah, so we've got the grad dot product of the mean flux, okay? So I'm only using one direction, so I'm just saying what's basically the convergence of the flux, because the convergence of flux tells me how fast the quantity is changing. And so the gradient of that flux, I differentiate that, is minus K, and then the second differential. Yeah? And then I can substitute this back into my original equation. Okay. So what do we see now? Now we have the same equation, but it's all written in terms of the grid box mean quantities. Okay. So my function h has turned this unknown subgrid scale variability into a parametrization based on the grid mean quantities by making a hypothesis that the statistics of the turbulence act to smooth out gradients on the large scale and the small scale. Okay, and this is the more general form. But now we've got a constant to specify. Okay, in order to close these equations, we have an unknown parameter, K. Okay. Now, how do we set K? Well, I can try and go out to lots of different locations and try and measure the average turbulent activity, and I can take that value of K. But of course, I'm never going to know it exactly, because maybe I can measure it here, and I can measure it in Ghana, and I can measure it at a location in Brazil, but I can't measure it all over the planet, everywhere, at all times. So I'm only sampling the turbulence. So my K that I derive from observations, for example, will be an approximate value. And I can put it into the model, and then maybe I'll find that if I adjust K by 10% upwards, my weather forecast is a little bit better. If I decrease it down by 10%, it may be a little bit worse. Maybe then next year when I change another aspect in the model, maybe the radiation scheme, or I change the advection scheme, or I change the grid box sizes, I might find that a different value of K gives me the best results. And so then I change it back up a little bit. That process of choosing your value of K to give you the best results is known as tuning. So if you ever hear people talking about tuning, this is the process we're talking about. Now, it's not to say that K is completely random. You can take experimental values, like I said, to try and measure K, but you don't know it exactly. There's an error bar on that value. And so you're within your rights. It's justified then to try and change it within your observational error to try and improve the forecast. This is tuning. Okay. Parameterizations don't just have normally one K. There might be lots of unknown values. Some of them are known quite precisely, in which case you can only change them a little way justifiably with your tuning. Some of these parameters are very unknown. You have a very bad idea of where they can be set. So really have a wide range. So now if you hear people talking about tuning, you know what they mean. It means you have a constant or a parameter inside a parameterization, and you don't know exactly how to set that parameter. And so you're tuning to change it within your best guess of what the range should be in order to try and improve the simulation of the climate, measured by the metric. I haven't even talked about validation. So that could be, for example, the average cloud cover, the variability year to year of the temperature, your representation of ENSO variability. There's a whole list that's infinitely long of the different ways in which you can measure the quality of your simulation. Okay. And it might depend on the purpose of that simulation. If there's a weather forecast, you might want to have the low pressure systems arriving at the right time. With a climate model, it may be the prediction of a drought index over Africa. It depends on what you're interested in, what the purpose of the simulation is. So that's tuning.
Okay, I have a question. So in a certain model, does it mean that the more
Not necessarily, and there is a tendency to throw complexity at parameterizations, and sometimes it's like sometimes people think that more complicated is better. More complicated often means more tunable parameters, and I think what it means is if you have more tunable parameters, you can perhaps minimize the error, but perhaps for the wrong reasons. Okay, I actually think it's best to try and unify these assumptions together, okay, into as few as parameters as possible. That's quite a complicated issue, so I prefer to talk about that after the lesson on the board if we can, because that I can get it. That's quite complicated, but yeah, you are right. It is a question, and adding more of these parameters means you have more tunable control, but you're also maybe not actually getting more accurate in terms of your representation.
Yeah, maybe before we go, considering that, for example, for this particular case, when we go back to the way we chose K,
Yes.
how K came into our equation. But if you found out at the end that if this K is positive, maybe it gives a better result, and when you make it that side, it will completely change your initial.
Yeah, I mean, like I say, you want to try and measure these parameters as best as you can. But I'm going to talk about this K now, this issue. So I said that we choose K to be a constant. Okay? So by choosing it to be a constant, I'm assuming that the turbulent activity is the same everywhere at all times. Okay. So let's imagine now that I set you the homework task of improving this parameterization. We want to make it better. How could we do that? What would be one way to try and improve this? So one of the weaknesses is maybe this a constant K approximation, yeah? So how could we improve this, do you think, just in a very descriptive way? What do you think would be a way of trying to improve K? Okay, so the data tells us that K will change from place to place, okay, as a function. So at the moment we've chosen it to be a constant, so what could we do? We could actually, do we want to break this assumption? What do you think? Yeah. Okay, so we can make K a function of, but what we're going to make it of space, but we don't want necessarily an unknown, so we're going to perhaps follow this approach, yeah? We want to make it a function of the grid scale variables. And we can see that, I mean, we've got the horizontal gradient, just as an example here, but for K, let's imagine, so K is measuring the activity of the turbulence. So for example, when you come in to land on an airplane, is it over land? We're landing over land, because most airports, of course, are not over sea, except for a few places like, I think, Hong Kong has one that stretches out over the sea. But if you come to land over land, is it more bumpy during the day or at night? During the day, because during the day, the sun is heating the surface strongly, and so that warm air is rising, so we have more bumpiness over the day. So let's think for a moment about which parameter would we actually relate K to. So when we have hot heating of the surface and colder air above, we have more bumpiness, yeah? So what would we relate K to in the model? Temperature. But what aspect of temperature? Yeah, exactly, the vertical gradient. So we can make K a function of the vertical gradient of temperature. If it's getting colder more quickly in the vertical, okay, and in fact if we have unstable conditions, we expect to have strong mixing. At night, sometimes you don't have any bumpiness in the airplane at all, because at night sometimes the surface cools off. The air above it is actually warmer, and so it's very stable. So the air is completely still, and we don't have any turbulence, in which case K would be 0. We don't have any mixing at all anymore. It doesn't matter how strong the gradient is. If the air is not moving at all, it's completely still, we don't have any mixing. Very good. That was one of the earliest evolutions of these parameterizations. K originally was constant in the 1960s. The next step was to make it a function of the vertical gradient of temperature. And then that was taken further and further with more complicated stability functions. So it wasn't just a linear function of the gradient of temperature, it becomes a nonlinear function. You make more observations to try and work out what that function should look like as a function of stability, as a function of the wind shear, because it's not just the temperature gradient. If you have strong wind shear with a small horizontal wind here and a strong horizontal wind there, it tends to roll the air over. So the wind, you can add not just the temperature, but also the wind shear, how the wind changes in height. And that's how these parameterizations evolve. Nice, no? You should all be excited now. The magic of parameterization, yeah? Okay, so we're almost out of time. Okay, we've already done this. Excellent. So what I'm going to do at the beginning of tomorrow's lesson, I'm going to talk about another example of cloud parameterization. Okay. And then I might talk a little bit about uncertainty of models, so ensemble forecasting. It depends on our time constraints, okay? And we'll have a little bit of time for discussion as well, but I'm going to finish there today. Are there any questions about that?
It's already uniform, so maybe just in a nearby place there is a lot of change, so we need to resolve. We need more resolution. So how do we take care of such things changes? In some places it is uniform, in another place there is, for example, just windstorms.
Well, I mean, let's think for a moment. I think the question, if I understand it, is where would you normally get the best improvement by increasing the resolution, if I understand it. And so, I mean, let's think about it together. Where do you think the greatest benefit you would expect to have of increasing resolution? It's not always the way it works, but where would we expect to have the greatest benefit of decreasing the box size? When we have high, fast-changing topography of mountains. So representing those mountains more accurately would perhaps improve the forecast model there. But even over areas where you don't have fast-changing topography, so for example, over the oceans, you don't have any topography at all. Nevertheless, if you have like convection in one location, you can have very strong gradients in the water vapor in the atmosphere. Okay. So in fact, I will try and find a simulation of an example where you can get these kind of wispy filaments where the total column water vapor can change by a factor of 3, 4, or 5 within the space of just a few tens of kilometers. And so if you don't have a high resolution, you can't resolve those changes, and they will affect the way that radiation is interacting, how much solar radiation actually is absorbed in the vertical, and the way that convection is organizing. So there are many ways to try and approach this. Some models, in fact, now have actually tried to introduce adaptive grids or stretched grids. So you can have adaptive grid models where instead of having regular box sizes, the boxes refine and actually become smaller in locations where there's a lot of things going on. If you have a lot of motion and storm activity, then the boxes will shrink there to try and represent that. And in other areas where the flow is very laminar and linear, then you have larger box sizes. So those methods have been refined for, should we say, regional scale models, but they're not widely employed. And the reason why is often the overhead. And what I mean is the calculations you have to do to work out where you reduce the box size, where you leave it. Often that overhead of those calculations to actually run that system use up more power than you gain by having small resolution in one place and a large box in another place. So often the calculation of trying to refine the mesh and leave it larger elsewhere uses more power than simply just using a small box everywhere. because the small box everywhere takes more power, but you don't have all of the overhead, should we say, of the calculations. Okay, I need small boxes there, large boxes there. And also, you have a problem sometimes of stability. Where you have small boxes, you need a small time step. Where you have large boxes, you can have a large time step. But that's quite complicated. You know, one part of the globe is being stepped with small time steps and another part with large time steps. So what you end up doing often is you anyway, even with the large boxes, you still use the same small time step. So you're still wasting some time there. So those methods have not been that widely employed, but I know there's 2 research groups, especially NCAR and Boulder, where they're still working on that, of that kind of grid refinement. The other nice thing is that they're looking at ways of trying to actually try and have schemes that try and resolve at least some of the aspects of the motion by having small models with small boxes placed inside the big boxes, so super parameterizations. At the end of the day, I think the ultimate solution will be in the next, at least the next 10 years, this kind of picture here on the front of the notes. I mean, within the next 10 years, weather forecasts will be done globally with boxes that will be able to actually resolve the motions. So they'll be run with boxes on the order of 1 to 2 kilometers globally. Okay. We're not quite there yet, but they're down to like 15 kilometers. They'll be down to 10 kilometers within the next year. And so this is not out of the reach of weather forecast models, but it won't be within reach of climate models unless there's a massive increase in the investment into computing that's available for climate integration. So climate models will still have these, and even with 2 kilometers, you still need parameterizations for all of the microphysics. So even if you have the mean motion in the updrafts resolved, in other words, you can represent the updraft inside the cloud, the actual processes of all the droplet formation, the ice crystal freezing, the rainfall falling, will still need to be parameterized by these simple models. And I'm going to talk about some of those tomorrow. Okay, I'll stop there.